What if the universe's most mysterious objects, black holes, are not what we think they are? Imagine a place where time bends, light vanishes, and the laws of physics, as we know them, break down. Black holes have fascinated scientists and dreamers alike for decades. But what if everything we've learned so far is just the tip of the cosmic iceberg? Today, we're diving into 25 groundbreaking theories about black holes that could completely reshape our understanding of the universe. From the possibility of black holes being gateways to other dimensions to the idea that they might hold the key to dark matter, these theories challenge everything we thought we knew. So, if you're ready to explore the edges of science and imagination, stay with us. By the end of this video, you'll discover ideas so mind-bending, they might just change the way you see the cosmos forever. Let's begin. Now, let's step into the first theory, one that sounds like it's straight out of science fiction, but is grounded in real scientific exploration. The idea that black holes could be wormholes, gateways to other universes or distant regions of space, is a concept that has captivated both physicists and dreamers. At the heart of this theory is the notion that black holes might not just be cosmic vacuum cleaners, but rather tunnels through the fabric of space-time. Imagine a shortcut across the universe where you could enter a black hole in one part of the cosmos and emerge in another galaxy, or even another universe entirely. This is the essence of the wormhole theory. To understand how this could work, we need to look at the science of wormholes. In simple terms, a wormhole is a theoretical passage through space-time that creates a shortcut between two distant points. Think of it like folding a piece of paper so that 2 points touch, then poking a hole through them. That hole would be the wormhole. According to Einstein's theory of general relativity, such structures could exist, but they would require something called exotic matter to stay open. Exotic matter is a hypothetical substance with negative energy, which could counteract the immense gravitational forces that would otherwise collapse the wormhole. But here's where it gets even more fascinating. Some scientists believe that black holes, with their intense gravitational pull and warping of spacetime, might naturally form the entrance to a wormhole. The event horizon, the point of no return around a black hole, could act as the gateway. However, this idea challenges traditional physics in a big way. For one, we don't yet know if exotic matter exists, or if it's even possible to create or harness it. Additionally, the extreme conditions inside a black hole, including the singularity at its core, make it unclear whether anything could survive the journey through a wormhole, let alone emerge intact on the other side. Despite these challenges, the wormhole theory continues to inspire research and debate. It pushes the boundaries of our understanding of space-time, gravity, and the very nature of the universe. Could black holes really be cosmic shortcuts, or is this just a tantalizing idea that will remain in the realm of theory? Either way, it's a reminder of how much we still have to learn about these enigmatic objects. And with that, let's move on to the next theory, where we'll explore another mind-bending possibility about black holes. Now, let's take a closer look at the evidence that keeps the wormhole theory alive despite its many challenges. One intriguing piece of the puzzle comes from the world of quantum entanglement, a phenomenon where two particles become linked, no matter how far apart they are in the universe. Some researchers suggest that this mysterious connection might hint at the existence of wormholes. In fact, there's a hypothesis that entangled particles could be connected by tiny, microscopic wormholes, acting as bridges through space-time. While this idea is still speculative, it offers a fascinating way to think about how wormholes might operate on a quantum level. Another key piece of evidence comes from the way black holes warp spacetime. According to Einstein's theory of general relativity, massive objects like black holes create deep curves in the fabric of spacetime. These curves are so extreme that they could, in theory, connect distant regions of the universe or even different universes altogether. Simulations and mathematical models have shown that under certain conditions, black holes could form the entrances to wormholes. However, these models often rely on assumptions like the existence of exotic matter, which we've yet to discover or fully understand. But let's not forget the challenges. One of the biggest hurdles is the sheer instability of wormholes. Even if they could form, keeping them open would require exotic matter with negative energy, something that defies our current understanding of physics. Without it, any potential wormhole would collapse almost instantly. Then there's the question of survival. The intense gravitational forces near a black hole's singularity would likely tear apart anything trying to pass through, making the idea of traveling through a wormhole seem impossible, at least with our current knowledge. Skepticism also surrounds the practicality of wormholes. Even if they exist, could we ever detect them? And if we could, would they lead anywhere meaningful? These questions remain unanswered, leaving the wormhole theory in a fascinating but uncertain place. Yet, it's this very uncertainty that drives scientists to keep exploring, pushing the boundaries of what we know about the universe. As we move forward, the next theory takes us into even more controversial territory, where black holes might not be as serene as they seem. Stay tuned as we explore the idea of black hole firewalls and how they could rewrite the rules of physics. Now, shifting our focus to a theory that challenges everything we thought we knew about black holes, let's dive into the concept of black hole firewalls. Imagine approaching the edge of a black hole, expecting to cross the event horizon, the point of no return, only to be met with a blazing wall of energy. This is the essence of the firewall theory, a radical idea that suggests black holes might not be as calm and predictable as we once believed. Instead, they could be surrounded by a fiery barrier of intense radiation, capable of incinerating anything that comes too close. The firewall theory emerged as a potential solution to one of the most perplexing problems in physics, the information paradox. According to quantum mechanics, information about the universe can never be destroyed. Yet, black holes seem to defy this rule. When matter falls into a black hole, it's thought to be lost forever, crushed into a singularity. But if information can't be destroyed, where does it go? This paradox has puzzled scientists for decades, and the firewall theory offers a bold answer. It proposes that the information isn't lost, it's burned up at the event horizon, releasing energy in the form of a firewall. But how does this work? The idea hinges on the behavior of particles near the event horizon. In quantum physics, particles and their antiparticles can spontaneously appear and annihilate each other. Near a black hole, one of these particles might fall in while the other escapes, creating what's known as Hawking radiation. The firewall theory suggests that this process isn't as smooth as we thought. Instead, the escaping particles could create a violent burst of energy, forming a firewall that destroys anything trying to cross the event horizon. This theory, while intriguing, is far from universally accepted. It directly contradicts Einstein's theory of general relativity, which predicts that crossing the event horizon should be uneventful, a concept known as the no-drama principle. According to general relativity, an observer falling into a black hole wouldn't notice anything unusual at the event horizon. The firewall theory, however, turns this idea on its head, suggesting that the event horizon is anything but calm. Critics argue that firewalls would violate the principles of quantum mechanics and general relativity, creating more problems than they solve. If firewalls exist, they would require a complete overhaul of our understanding of black holes and the laws of physics. Yet, the theory has sparked intense debate and inspired new research, pushing scientists to explore the boundaries of what's possible. As we continue to unravel the mysteries of black holes, the firewall theory reminds us that the universe is full of surprises. It challenges us to rethink our assumptions and consider possibilities that once seemed unimaginable. Next, we'll explore how this controversial idea could reshape our understanding of quantum mechanics and general relativity. and why it remains one of the most hotly debated topics in modern physics. Now, let's take a closer look at how the firewall theory could fundamentally alter our understanding of two pillars of modern physics: quantum mechanics and general relativity. If firewalls exist, they would force us to rethink some of the most deeply held principles in these fields. For instance, general relativity describes gravity as the curvature of spacetime, predicting that crossing the event horizon of a black hole should be a smooth, uneventful process. But the firewall theory challenges this by suggesting that the event horizon is anything but calm. It's a violent, energetic barrier. This contradiction raises a critical question: can these two theories coexist, or do we need a completely new framework to explain black holes? The implications for quantum mechanics are equally profound. Quantum theory tells us that information cannot be destroyed, yet black holes seem to erase it entirely. The firewall theory attempts to resolve this paradox by proposing that information is converted into energy at the event horizon, effectively preserving it in a different form. However, this idea introduces its own set of challenges. For example, how does the firewall reconcile with the principle of locality, which states that physical processes only affect their immediate surroundings? If a firewall exists, it would imply that information is being processed in a highly non-local way, which goes against the grain of traditional quantum mechanics. Another layer of complexity comes from the mathematical models used to describe black holes. General relativity and quantum mechanics rely on different sets of equations, and so far, no one has successfully unified them into a single, coherent theory. The firewall theory highlights this gap, forcing physicists to confront the limitations of our current understanding. It's not just about black holes, it's about the very nature of reality. Could firewalls be a clue to a deeper, more unified theory of physics? Or are they a sign that we're missing something fundamental about how the universe works? Despite its challenges, the firewall theory has sparked a wave of new research and debate. Scientists are exploring alternative ideas, such as the possibility that firewalls might only form under specific conditions or that they could be a temporary phenomenon. Others are investigating whether the theory could be modified to better align with both quantum mechanics and general relativity. What's clear is that the firewall theory has reignited the conversation about black holes, pushing the boundaries of what we thought was possible. As we continue to grapple with these questions, one thing is certain: the firewall theory has opened up new avenues for exploration. It reminds us that the universe is far more complex and mysterious than we often assume. And while the debate is far from settled, the very existence of this theory shows how science thrives on challenging ideas and seeking answers to the unknown. Next, we'll turn our attention to another groundbreaking theory, one that suggests black holes might be the key to understanding dark matter, the invisible substance that makes up most of the universe's mass. Now, shifting our focus to another fascinating idea, let's explore the theory that black holes might be the cosmic factories producing dark matter. Dark matter, as you may know, is the invisible substance that makes up about 85% of the universe's mass. Yet, despite its overwhelming presence, we still don't fully understand what it is or where it comes from. This theory suggests that black holes could hold the key to solving this mystery. The idea revolves around the possibility that black holes, with their immense gravitational pull and extreme environments, might be generating dark matter particles. These particles could be created through processes happening near the event horizon or even within the black hole itself. Some scientists propose that as matter falls into a black hole, it could undergo transformations that produce dark matter, releasing it back into the universe. This would mean that black holes aren't just cosmic vacuum cleaners, they're also potential creators of the very substance that shapes the cosmos. What makes this theory particularly intriguing is how it connects two of the universe's greatest mysteries, black holes and dark matter. If black holes are indeed producing dark matter, it could explain why we've struggled to detect dark matter directly. instead of searching for it in isolation, we might need to look at black holes as the source. This would fundamentally change our approach to studying both phenomena, opening up new avenues for research and discovery. Of course, like any groundbreaking theory, this idea comes with its share of challenges. For one, we still don't know exactly what dark matter is made of, which makes it difficult to test whether black holes are producing it. Additionally, the mechanisms by which black holes could generate dark matter are still largely speculative. However, the theory has sparked significant interest, with researchers exploring mathematical models and simulations to see if this connection holds up. As we continue to probe the depths of space, this theory reminds us that black holes are more than just destructive forces. They could be essential players in the cosmic balance. By potentially producing dark matter, they might be shaping the very fabric of the universe in ways we're only beginning to understand. Next, we'll dive into the evidence that supports this theory, examining the observations and simulations that suggest black holes and dark matter might be more connected than we ever imagined. Now, let's turn our attention to the evidence that gives weight to this intriguing theory. Over the past few years, astronomers and physicists have been piecing together observations and running simulations that hint at a possible connection between black holes and dark matter production. One of the most compelling pieces of evidence comes from the behavior of galaxies. Scientists have noticed that galaxies with supermassive black holes at their centers tend to have higher concentrations of dark matter. This correlation suggests that black holes might be influencing the distribution of dark matter or even contributing to its creation. Another fascinating observation involves the way black holes interact with their surroundings. When matter falls into a black hole, it doesn't just disappear, it releases energy in the form of radiation and jets of particles. Some researchers believe that during this process, dark matter particles could be generated and ejected into space. Simulations of black hole environments have shown that under extreme conditions, such as those near the event horizon, particles with properties similar to dark matter could form. These simulations, while still theoretical, provide a plausible framework for how black holes might produce dark matter. Gravitational wave observations have also added to the intrigue. When black holes collide, they send ripples through spacetime that we can detect here on Earth. Some scientists speculate that these collisions could release bursts of dark matter into the universe. While we haven't directly detected dark matter in these events, the data from gravitational wave observatories like LIGO and Virgo are being carefully analyzed for any hints of this elusive substance. Additionally, studies of the cosmic microwave background, the faint glow left over from the Big Bang, have revealed patterns that could be linked to dark matter. Some models suggest that black holes, particularly in the early universe, might have played a role in shaping these patterns by producing dark matter. This idea is still being explored, but it offers a tantalizing possibility that black holes have been influencing the universe's structure since its earliest moments. While these observations and simulations are promising, they also highlight the challenges of studying something as mysterious as dark matter. The evidence is indirect, and much of it relies on interpreting complex data. However, the growing body of research suggests that black holes could indeed be connected to dark matter in ways we're only beginning to uncover. As we gather more data and refine our models, this theory could transform our understanding of both black holes and the invisible substance that shapes the cosmos. Next, we'll explore another groundbreaking idea: the concept of black hole stars, where a black hole exists at the heart of a massive star, and how this could explain some of the universe's most puzzling phenomena. Now let's shift our gaze to a truly mind-bending concept: black hole stars. Imagine a star so massive, so dense, that it harbors a black hole at its very core. These hypothetical objects, known as black hole stars, could be the key to unlocking some of the universe's most puzzling mysteries. Unlike ordinary stars, which generate energy through nuclear fusion in their cores, black hole stars would have a black hole sitting at their heart, devouring matter and releasing energy in ways we're only beginning to understand. The idea of a black hole star challenges our traditional understanding of stellar evolution. Normally, when a massive star exhausts its fuel, it collapses under its own gravity, leading to a supernova explosion and potentially forming a black hole. But in the case of a black hole star, the black hole forms while the star is still active, creating a bizarre hybrid object. The outer layers of the star continue to shine brightly, while the black hole at its core consumes matter and emits powerful radiation. This unique combination could explain some of the strange phenomena astronomers have observed, such as ultra-bright objects that don't fit neatly into existing categories. One of the most intriguing possibilities is that black hole stars could be the source of certain types of gamma-ray bursts, some of the most energetic events in the universe. These bursts, which can outshine entire galaxies for a brief moment, are thought to originate from the collapse of massive stars or the merger of neutron stars. But a black hole star, with its intense gravitational pull and rapid consumption of matter, could produce even more extreme conditions, leading to bursts of energy that defy our current models. Another fascinating aspect of black hole stars is their potential role in the early universe. Some scientists speculate that these objects could have formed shortly after the Big Bang, when the first stars were incredibly massive and short-lived. If black hole stars existed in this era, they might have influenced the formation of galaxies and the distribution of matter in ways we're only now beginning to explore. Their immense gravitational pull could have acted as cosmic anchors, drawing in gas and dust to form the first structures in the universe. Of course, the concept of black hole stars is still highly theoretical, and detecting them poses significant challenges. Their outer layers would look like a normal star, making it difficult to distinguish them from ordinary stellar objects. However, advances in observational technology, such as more sensitive telescopes and improved data analysis techniques, could one day allow us to identify these cosmic oddities. If we do, it would open up a whole new chapter in our understanding of stars, black holes, and the universe itself. As we continue to explore the mysteries of black hole stars, we're reminded once again of how much we still have to learn about the cosmos. These objects, if they exist, could reshape our understanding of stellar physics and the forces that shape the universe. Next, we'll delve into how black hole stars might form and the challenges scientists face in detecting these elusive cosmic hybrids. Now, let's take a closer look at how black hole stars might come into existence and why spotting them in the vastness of space is no easy task. The formation of these cosmic hybrids begins with an incredibly massive star, one that dwarfs even the largest stars we've observed. In the early stages, such a star would burn through its nuclear fuel at an astonishing rate, generating immense heat and pressure in its core. But here's where things take a dramatic turn. Instead of collapsing into a supernova at the end of its life, the star's core could collapse directly into a black hole while the outer layers remain intact. This process would create a black hole star, a celestial object that defies conventional stellar evolution. The key to this formation lies in the star's sheer mass. If a star is massive enough, its core could reach the critical density required to form a black hole before the outer layers have a chance to explode or disperse. This would leave the black hole embedded within the star, surrounded by a shell of gas and plasma that continues to shine brightly. The result is a star that looks ordinary from the outside but harbors a black hole at its heart, a cosmic paradox that challenges our understanding of how stars live and die. Detecting these enigmatic objects, however, is a monumental challenge. From a distance, a black hole star would appear almost indistinguishable from a regular star. Its outer layers would emit light and heat just like any other star, making it nearly impossible to spot the black hole lurking within. scientists would need to look for subtle clues, such as unusual patterns in the star's radiation or gravitational effects that hint at the presence of a black hole. For instance, the black hole's intense gravitational pull could cause the star's outer layers to behave in unexpected ways, creating ripples in space-time or emitting bursts of energy that don't align with typical stellar activity. Another potential detection method involves studying the star's motion. A black hole star might exhibit slight wobbles or irregularities in its orbit caused by the black hole's gravitational influence. Advanced telescopes and instruments, like those capable of measuring gravitational waves or detecting faint variations in starlight, could provide the precision needed to identify these anomalies. Yet, even with cutting-edge technology, the search for black hole stars remains a daunting task, requiring both patience and ingenuity. The hunt for these cosmic hybrids is further complicated by their rarity. If black hole stars do exist, they are likely few and far between, formed under specific and extreme conditions that are difficult to replicate or observe. This makes them not only fascinating but also incredibly elusive, adding to the mystery that surrounds them. Despite the challenges, the potential discovery of a black hole star would be a groundbreaking moment in astronomy, offering new insights into the life cycles of stars and the behavior of black holes. As we continue to push the boundaries of our observational capabilities, the possibility of uncovering these hidden cosmic treasures grows ever closer. The search for black hole stars is a reminder of how much we still have to explore and how the universe continues to surprise us with its complexity. Next, we'll turn our attention to another intriguing theory: the idea that black holes could manipulate time, potentially acting as natural time machines. Now, let's shift our focus to one of the most mind-bending ideas in modern physics: the possibility that black holes could act as natural time machines. Imagine a place where the very fabric of time bends and twists, creating pathways that defy our everyday understanding of reality. This is the realm of black holes, where the laws of physics as we know them are pushed to their limits. At the heart of this theory lies the concept of time dilation, a phenomenon predicted by Einstein's theory of general relativity. Near a black hole, the gravitational pull is so intense that it warps spacetime itself. For an outside observer, time would appear to slow down dramatically for anything approaching the event horizon, the point of no return. This means that if you were to watch someone falling into a black hole, their movements would seem to stretch out, almost as if they were moving in slow motion. But for the person falling in, time would feel normal, creating a bizarre disconnect between their experience and what an observer sees. This extreme distortion of time opens up the tantalizing possibility of time travel. If you could somehow survive the journey into a black hole, you might find yourself in a region where time loops back on itself. In theory, this could allow for closed time-like curves, paths through spacetime that return to their starting point. These loops could, in essence, create a way to travel back in time. While this idea sounds like science fiction, it's grounded in the mathematics of general relativity, which allows for such exotic possibilities under extreme conditions. However, the challenges are immense. First, surviving the journey into a black hole is for now beyond our capabilities. The tidal forces near a black hole would stretch and compress anything that gets too close, a process known as spaghettification. Second, even if you could navigate these dangers, the nature of time travel within a black hole remains speculative. Scientists are still grappling with how to reconcile these ideas with the laws of quantum mechanics, which govern the behavior of particles at the smallest scales. Despite these hurdles, the idea of black holes as time machines continues to captivate scientists and science fiction enthusiasts alike. It raises profound questions about the nature of time itself. Could time travel ever become a reality? And if so, what would that mean for our understanding of cause and effect? These are questions that push the boundaries of human knowledge, reminding us of how much we still have to learn about the universe. As we ponder these possibilities, it's worth noting that black holes aren't just cosmic oddities, they're windows into the deepest mysteries of space and time. The next time you look up at the night sky, consider this. Somewhere out there, a black hole might be bending time itself, creating pathways to moments long past or yet to come. It's a thought that challenges our imagination and invites us to explore the unknown. Next, we'll delve into the theoretical frameworks that make this idea possible, examining the physics behind time dilation and how it fits into the broader conversation about time travel. Now, let's take a closer look at the theoretical frameworks that make the idea of black holes as time machines possible. At the core of this concept is Einstein's theory of general relativity, which describes how massive objects like black holes warp the fabric of space-time. This warping isn't just a distortion of space, it also affects time. Near a black hole, the gravitational field is so strong that it causes time to slow down relative to an observer far away. This effect, known as gravitational time dilation, is one of the key ingredients in the recipe for potential time travel. To understand how this works, imagine two clocks, one placed near a black hole and another far away in a region of weak gravity. The clock near the black hole would tick more slowly compared to the one far away. Over time, this difference would grow, creating a gap between the two clocks. If you could somehow move between these two regions, you might experience time passing at different rates, effectively allowing you to travel into the future relative to someone else. This isn't science fiction, it's a real phenomenon that has been observed in experiments with atomic clocks here on Earth, though on a much smaller scale. But what about traveling into the past? This is where things get even more intriguing. Some solutions to Einstein's equations suggest the existence of closed time-like curves, paths through spacetime that loop back on themselves. In theory, if you could follow such a curve, you might return to a point in your own past. Black holes, with their extreme gravitational fields, are one of the few places in the universe where these curves could potentially exist. However, the conditions required for this are so extreme that they remain purely theoretical for now. One of the biggest challenges in making sense of these ideas is reconciling them with quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. Quantum mechanics introduces uncertainty and randomness into the mix, which complicates the neat predictions of general relativity. For example, the concept of a closed time-like curve raises questions about causality, the idea that cause must always precede effect. If time travel were possible, could you go back and change the past? And if so, what would that mean for the future? These are questions that physicists are still grappling with, and they highlight the need for a unified theory that can bridge the gap between general relativity and quantum mechanics. Despite these challenges, the idea of black holes as time machines continues to inspire both scientists and dreamers. It's a reminder of how much we still have to learn about the universe and the strange, beautiful ways it operates. As we explore these theoretical frameworks, we're not just pushing the boundaries of science, we're also challenging our understanding of reality itself. Next, we'll dive into another fascinating theory, the possibility that black holes might function as natural quantum computers, processing information in ways we're only beginning to understand. Now, shifting our focus to another mind-bending idea, let's explore the possibility that black holes might be the universe's most powerful quantum computers. This theory suggests that black holes don't just consume matter and energy, they might also process information in ways that defy our current understanding of physics. At first glance, this might sound like science fiction, but when we dig deeper, it's rooted in some of the most cutting-edge ideas in quantum mechanics and general relativity. To grasp this concept, we need to think about how black holes handle information. According to the laws of quantum mechanics, information can never be destroyed, it can only be transformed. But black holes, with their immense gravitational pull, seem to challenge this principle. When matter falls into a black hole, it appears to vanish from the universe, taking its information with it. This creates what's known as the black hole information paradox, a puzzle that has stumped physicists for decades. One proposed solution is that black holes don't actually destroy information, they store and process it. Imagine a black hole as a kind of cosmic hard drive, encoding information on its surface or event horizon in a way that's similar to how a hologram works. This idea, known as the holographic principle, suggests that all the information about what falls into a black hole is preserved on its boundary. From there, the black hole might act like a quantum computer, performing complex calculations with this stored information. But how could this work? Quantum computers, as we know them, rely on qubits, tiny units of information that can exist in multiple states at once. In a black hole, the extreme conditions near the event horizon might create a natural environment for quantum processes to occur. Some scientists speculate that the chaotic, high-energy environment of a black hole could allow for the spontaneous emergence of quantum computing-like behavior, processing information in ways we can't yet replicate or fully understand. This theory isn't just about solving a paradox, it could have profound implications for our understanding of the universe. If black holes are indeed natural quantum computers, they might hold the key to unlocking the mysteries of quantum gravity, the elusive theory that aims to unite general relativity and quantum mechanics. By studying black holes, we might gain insights into how information is processed on the most fundamental levels of reality. Of course, this idea is still in its early stages, and there's much we don't know. For example, how exactly does a black hole encode and process information? And what would the output of such a quantum computation look like? These are questions that physicists are actively exploring, using tools like string theory and advanced simulations to push the boundaries of our knowledge. As we continue to unravel the mysteries of black holes, the idea that they might function as quantum computers opens up a whole new realm of possibilities. It's a reminder that the universe is far stranger and more complex than we can imagine, and that black holes, with their immense power and mystery, might hold secrets that could revolutionize our understanding of physics. Next, we'll delve into another fascinating theory: the possibility that black hole collisions could reveal hidden dimensions of space as predicted by string theory. Now, let's take a closer look at how black holes might store and process information, and what this could mean for the future of quantum computing. If black holes are indeed natural quantum computers, the way they handle information could be unlike anything we've ever encountered. One of the most intriguing aspects of this theory is the idea that black holes might encode information on their event horizons. Think of it like this: the event horizon, the boundary around a black hole from which nothing can escape, could act as a kind of cosmic storage device. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, a black hole might encode all the information about the matter and energy it consumes on its surface. This concept, known as the holographic principle, suggests that the information isn't lost. It's just stored in a way that's completely foreign to our everyday experience. But how does this information get processed? In a traditional quantum computer, qubits, the basic units of quantum information, are manipulated to perform calculations. In a black hole, the extreme gravitational forces and chaotic environment near the event horizon might create conditions where quantum processes occur naturally. Some scientists speculate that the interactions between particles and the intense curvature of spacetime could allow the black hole to perform computations on the information it stores. These computations wouldn't be like the ones we're familiar with. They'd be far more complex and potentially beyond our current understanding. The implications of this are staggering. If black holes can process information in this way, they might be the most powerful computers in the universe. They could be performing calculations that would take our most advanced supercomputers billions of years to complete, if we could even figure out how to replicate them. This could open up entirely new avenues for understanding quantum mechanics and gravity, potentially leading to breakthroughs in fields like quantum computing and theoretical physics. But there's still a lot we don't know. For instance, how exactly does a black hole encode information on its surface, and what would the output of these quantum computations look like? Some theories suggest that the information might be emitted as Hawking radiation, the faint glow of particles that black holes are thought to emit over time. If we could decode this radiation, it might give us a glimpse into the inner workings of a black hole's quantum processes. This theory also raises questions about the nature of reality itself. If black holes can store and process information in such a unique way, could they be revealing something fundamental about the fabric of the universe? Could the universe itself be a kind of quantum computer with black holes acting as its processors? These are questions that push the boundaries of our understanding and challenge us to think in entirely new ways. As we continue to explore these ideas, one thing is clear: black holes are not just cosmic vacuum cleaners. They might be the key to unlocking some of the deepest mysteries of the universe. And if we can understand how they store and process information, it could revolutionize not just our understanding of physics, but also the way we think about computing and the nature of reality itself. Next, we'll explore another groundbreaking idea: the possibility that black hole collisions could reveal hidden dimensions of space as predicted by string theory. Now, let's shift our focus to another mind-bending idea: the possibility that black hole collisions could uncover hidden dimensions of space. This theory, rooted in string theory, suggests that the violent mergers of black holes might provide clues about dimensions beyond the three we experience every day. String theory, one of the most ambitious frameworks in modern physics, proposes that the universe isn't just made up of the familiar three dimensions of space and one of time. Instead, it suggests there could be as many as 10 or even 11 dimensions, all curled up and hidden from our perception. But how could black hole collisions help us detect these extra dimensions? When two black holes collide, they create ripples in spacetime known as gravitational waves. These waves carry information about the objects that produce them, including their masses, spins, and even the shape of spacetime itself. According to string theory, if extra dimensions exist, they could subtly alter the way gravitational waves propagate. For example, some of the energy from the collision might leak into these hidden dimensions, causing the gravitational waves we detect to be slightly weaker or different than expected. This idea isn't just theoretical. Scientists are actively searching for these subtle signatures in the data collected by gravitational wave observatories like LIGO and Virgo. If they find evidence of extra dimensions, it would be a monumental discovery, reshaping our understanding of the universe and confirming one of the key predictions of string theory. But why would extra dimensions matter? For one, they could help unify the fundamental forces of nature. In our current understanding, gravity behaves very differently from the other forces, like electromagnetism or the strong nuclear force. String theory suggests that in higher dimensions, these forces might actually be different manifestations of the same underlying phenomenon. Discovering extra dimensions could bring us closer to a theory of everything, a single framework that explains all the forces and particles in the universe. Of course, this theory isn't without its challenges. Detecting the faint signals of extra dimensions in gravitational wave data is incredibly difficult, and some physicists remain skeptical about whether string theory is the right path forward. But even if the evidence remains elusive, the idea that black hole collisions could reveal hidden dimensions is a testament to how these cosmic events continue to push the boundaries of our knowledge. As we explore this theory further, it's worth considering what it would mean if we discovered extra dimensions. Would it change how we perceive reality? Could it open up new possibilities for space travel or communication? These are questions that remind us just how much we have yet to learn about the universe. Next, we'll dive into the evidence from gravitational wave observations and how they might support the existence of these hidden dimensions. Now, let's take a closer look at the evidence scientists are gathering from gravitational wave observations and how it might point to the existence of these elusive extra dimensions. When black holes collide, the resulting gravitational waves carry a wealth of information about the event, including details about the black holes themselves and the fabric of spacetime. But what if these waves also hold clues about dimensions we can't see? One of the key predictions of string theory is that extra dimensions could influence the way gravitational waves behave. For instance, if energy from the collision were to leak into these hidden dimensions, the gravitational waves we detect here in our three-dimensional space might appear slightly weaker or distorted. This subtle difference could be the smoking gun that proves extra dimensions exist. Gravitational wave observatories like LIGO and Virgo are incredibly sensitive instruments designed to pick up these tiny ripples in spacetime. By analyzing the data from black hole mergers, scientists are searching for anomalies that might hint at extra dimensions. For example, if the observed gravitational waves don't perfectly match the predictions of general relativity, it could suggest that some of the energy is escaping into higher dimensions. So far, no definitive evidence of extra dimensions has been found, but the search is far from over. Each new black hole merger detected provides more data to scrutinize, and as our instruments become even more precise, the chances of spotting these subtle effects increase. It's like trying to hear a faint whisper in a noisy room. Every improvement in technology brings us closer to isolating that whisper. What makes this search so exciting is the potential payoff. If scientists do find evidence of extra dimensions, it wouldn't just confirm a key aspect of string theory, it would revolutionize our understanding of the universe. It could explain why gravity is so much weaker than the other fundamental forces, or even open up new possibilities for how the universe operates on the smallest scales. Of course, the absence of evidence so far doesn't mean extra dimensions don't exist. It could simply mean that their effects are too subtle for our current technology to detect. Or perhaps they manifest in ways we haven't yet thought to look for. Either way, the search for extra dimensions through gravitational waves is a fascinating example of how black holes continue to challenge and expand our understanding of the cosmos. As we move forward, the next theory we'll explore takes us into the realm of black holes as cosmic sensors, examining how they might hide singularities from the rest of the universe. This idea, known as the cosmic censorship conjecture, raises intriguing questions about what lies beyond the event horizon and whether the universe itself has rules about what it allows us to see. Now, shifting our focus to another intriguing idea, let's dive into the concept of black holes as cosmic sensors. This theory, known as the cosmic censorship conjecture, proposes that black holes act as nature's way of hiding singularities, those infinitely dense and infinitely small points at their cores from the rest of the universe. In other words, black holes might be the universe's ultimate secret keepers, ensuring that the bizarre and unpredictable behavior of singularities remains hidden behind their event horizons. The cosmic censorship conjecture was first introduced by physicist Roger Penrose in the late 1960s as a way to address one of the biggest puzzles in general relativity, the nature of singularities. According to Einstein's theory, singularities are points where the laws of physics as we know them break down completely. Gravity becomes infinitely strong, space-time curves infinitely, and our understanding of reality simply falls apart. But here's the catch: singularities are supposed to be hidden from view, tucked safely behind the event horizon of a black hole. This is where the cosmic censorship conjecture comes in, suggesting that the universe has a built-in mechanism to prevent these singularities from being exposed to the outside world. Why is this idea so important? Well, if singularities were ever to become naked, meaning they existed without the protective cloak of an event horizon, it would create a scenario where the laws of physics as we understand them would no longer apply. Predictability would go out the window, and the universe would become a far more chaotic and unpredictable place. The cosmic censorship conjecture, in essence, acts as a safeguard, ensuring that the universe remains orderly and that the strange and extreme physics of singularity stays confined within black holes. But is this conjecture actually true? That's a question scientists are still trying to answer. While general relativity supports the idea that singularities are hidden, some theoretical models suggest that under certain extreme conditions, such as during the collision of two black holes, a naked singularity might briefly form. If this were to happen, it would challenge the cosmic censorship conjecture and force us to rethink our understanding of black holes and the nature of space-time itself. So far, no definitive evidence of naked singularities has been found, but the search continues. By studying black hole mergers and other extreme cosmic events, scientists hope to uncover whether the universe truly has this built-in censorship mechanism or if singularities might occasionally slip through the cracks. Either way, the cosmic censorship conjecture remains a fascinating and essential piece of the puzzle as we strive to understand the true nature of black holes and the universe they inhabit. As we move forward, the next theory we'll explore takes us into the realm of black holes and the multiverse, examining how these cosmic giants might serve as bridges to other universes. This idea opens up a whole new dimension of possibilities, challenging us to rethink not just black holes, but the very fabric of reality itself. Now, let's take a closer look at the mathematical backbone of the cosmic censorship conjecture and the debates it has sparked among physicists. At its core, this theory relies heavily on the equations of general relativity, which describe how massive objects like black holes warp spacetime. Mathematicians and physicists have spent decades trying to prove whether singularities must always be hidden behind event horizons, as the conjecture suggests. One of the key challenges lies in the fact that general relativity, while incredibly accurate in describing gravity, doesn't account for quantum mechanics, the rules that govern the behavior of particles at the smallest scales. This gap creates a fertile ground for debate. On one side of the argument, researchers have developed mathematical models that seem to support the idea of cosmic censorship. These models show that under most realistic conditions, singularities remain safely tucked away behind event horizons, preventing their chaotic influence from spilling out into the universe. For example, simulations of black hole collisions, events where the formation of a naked singularity might seem most likely, have so far failed to produce evidence of such an occurrence. This lends credibility to the idea that the universe has a built-in mechanism to keep singularities hidden. However, not everyone is convinced. Some theorists argue that the cosmic censorship conjecture might not hold true in all scenarios. For instance, certain highly idealized mathematical solutions to Einstein's equations suggest that naked singularities could in fact exist. These solutions often involve extreme conditions, such as black holes spinning at nearly the speed of light or collapsing stars with perfectly symmetrical properties. While these scenarios might seem far-fetched, they raise important questions about the limits of our current understanding. If even one of these solutions proves valid, it could mean that the universe isn't as orderly as the cosmic censorship conjecture suggests. The debate doesn't stop there. Some physicists have proposed alternative theories that challenge the very foundation of the conjecture. For example, string theory, a framework that attempts to unify general relativity and quantum mechanics, suggests that singularities might not be points of infinite density at all. Instead, they could be replaced by exotic structures that don't require censorship. These ideas, while still speculative, highlight the ongoing struggle to reconcile the strange behavior of black holes with our current understanding of physics. So, where does this leave us? For now, the cosmic censorship conjecture remains a compelling but unproven idea. It serves as a reminder of how much we still have to learn about black holes and the universe as a whole. As scientists continue to refine their models and gather new data, whether from gravitational wave detectors or advanced simulations, we may finally uncover whether the universe truly has a way of keeping its deepest secrets hidden. Until then, the debate over cosmic censorship will continue to inspire both curiosity and controversy in the world of theoretical physics. Next, we'll venture into the fascinating idea of black holes as bridges to other universes, exploring how these cosmic giants might connect us to realms beyond our own. This theory pushes the boundaries of our imagination, challenging us to rethink not just black holes, but the very nature of reality itself. Now, let's shift our gaze to an idea that stretches the limits of our imagination: black holes as gateways to other universes. This theory, rooted in the concept of the multiverse, suggests that black holes might not just be cosmic vacuum cleaners, but could instead serve as bridges connecting our universe to entirely different realms. Imagine stepping through a black hole and emerging in a universe with entirely different laws of physics, or perhaps one where time flows backward. It's a mind-bending idea, but one that has gained traction among some of the brightest minds in theoretical physics. At the heart of this theory lies the multiverse framework, which proposes that our universe is just one of countless others, each with its own unique properties. Black holes, with their immense gravitational pull and ability to warp spacetime, could act as natural portals between these universes. The idea isn't entirely new. It builds on the concept of wormholes, hypothetical tunnels through spacetime that could connect distant regions or even different universes. But while wormholes remain purely theoretical, black holes are very real, and their potential role in the multiverse adds a fascinating layer to their mystery. One of the key pieces of evidence supporting this idea comes from the study of singularities. As we've discussed earlier, singularities are points of infinite density at the center of black holes, where the laws of physics as we know them break down. Some theorists suggest that these singularities might not be dead ends, but could instead lead to other universes. In this scenario, the singularity acts as a kind of cosmic doorway, allowing matter and energy to pass through into a new realm. This idea is supported by certain solutions to Einstein's equations of general relativity, which hint at the possibility of space-time connections between universes. But how could we ever test such a theory? After all, if black holes truly are bridges to other universes, how would we even begin to observe or measure such a phenomenon? One approach involves studying the behavior of matter and energy near the event horizon of a black hole. If black holes are indeed gateways, they might leave behind subtle clues in the form of unusual radiation patterns or gravitational effects. For example, some researchers have proposed that the Hawking radiation emitted by black holes, a faint glow predicted by quantum mechanics, could carry information about the nature of these cosmic bridges. While this remains speculative, it offers a tantalizing avenue for future exploration. Of course, not everyone is convinced. Critics argue that the multiverse theory, while intriguing, lacks direct observational evidence. They point out that even if black holes do connect to other universes, the extreme conditions near a singularity would make it impossible for anything to survive the journey. Others suggest that the idea of a multiverse is more of a philosophical concept than a scientific one, at least until we find a way to gather concrete evidence. Despite these challenges, the idea of black holes as bridges to other universes continues to captivate scientists and enthusiasts alike. It challenges us to rethink not just the nature of black holes, but the very fabric of reality. Could our universe be just one of many, all interconnected by these cosmic gateways? As we continue to explore the mysteries of black holes, we may find that the answers lie not just within our own universe, but beyond it. Next, we'll delve into the evidence that might support the existence of parallel universes, examining how black holes could provide clues about the multiverse and what that means for our understanding of the cosmos. Now, let's turn our attention to the evidence that might link black holes to the existence of parallel universes. While the idea of a multiverse remains speculative, black holes could hold the key to uncovering clues about these alternate realities. One intriguing possibility lies in the study of gravitational waves, the ripples in space-time caused by massive cosmic events like black hole collisions. When two black holes merge, they send out gravitational waves that carry information about their properties. Some scientists suggest that these waves might also contain subtle hints about the nature of the multiverse, such as distortions or anomalies that could point to interactions with other universes. Another avenue of exploration involves the behavior of matter and energy near black holes. If black holes are indeed gateways to other universes, they might leave behind unique signatures in the form of unusual radiation or particle emissions. For instance, the Hawking radiation emitted by black holes, a faint glow predicted by quantum mechanics, could carry encoded information about the structure of space-time beyond our universe. While detecting such signals would be incredibly challenging, advancements in observational technology, like more sensitive telescopes and gravitational wave detectors, could bring us closer to uncovering these cosmic secrets. Additionally, the study of singularities, those infinitely dense points at the center of black holes, might offer further insights. Some theories propose that singularities could act as bridges between universes, with the extreme conditions at their cores creating pathways to alternate realities. While we can't directly observe singularities, mathematical models and simulations provide a way to explore these ideas. For example, certain solutions to Einstein's equations of general relativity suggest that singularities might not be dead ends but instead lead to other regions of spacetime, potentially within a multiverse framework. Critics, however, argue that the evidence for parallel universes remains indirect and largely theoretical. They point out that while black holes are fascinating objects, their connection to the multiverse is still a matter of speculation. Without direct observational proof, the idea of black holes as cosmic bridges remains a tantalizing hypothesis rather than a confirmed reality. Still, the pursuit of this theory pushes the boundaries of our understanding, challenging us to consider the possibility that our universe is just one piece of a much larger cosmic puzzle. As we continue to explore the mysteries of black holes, the search for evidence of parallel universes remains a thrilling frontier. Whether through gravitational waves, radiation patterns, or mathematical models, black holes may yet reveal clues about the existence of other realms beyond our own. And as we gather more data and refine our theories, we inch closer to answering one of the most profound questions in science. Are we alone in the cosmos, or is our universe just one of many? Next, we'll explore another groundbreaking idea, black holes as holograms, and how this theory could revolutionize our understanding of space, time, and reality itself. Now, let's dive into a theory that could completely reshape how we think about reality itself. The idea that black holes might function as holograms. This concept, known as the holographic principle, suggests that all the information about what falls into a black hole isn't lost forever but is instead encoded on its surface, much like a hologram. Imagine a holographic image where a three-dimensional picture is stored on a flat, two-dimensional surface. In a similar way, the holographic principle proposes that the vast complexity of a black hole's interior could be represented entirely on its outer boundary, the event horizon. The roots of this idea trace back to the work of physicists like Gerard T. Hooft and Leonard Susskind, who argued that the information about everything swallowed by a black hole isn't destroyed but is instead preserved on its surface. This challenges the traditional view that black holes are cosmic vacuum cleaners, sucking in matter and erasing it from existence. Instead, the holographic principle suggests that black holes are more like cosmic hard drives, storing information in a way we're only beginning to understand. One of the most fascinating aspects of this theory is how it ties into quantum mechanics and gravity. According to the holographic principle, the information on the surface of a black hole is encoded in tiny, discrete units, much like pixels on a screen. These units, often referred to as bits of information, could hold the key to reconciling the laws of quantum mechanics with Einstein's theory of general relativity, a problem that has puzzled scientists for decades. If true, this would mean that black holes aren't just mysterious objects in space, but could be the key to unlocking a deeper understanding of the universe itself. But how does this work in practice? Think of it like this. When an object falls into a black hole, its information isn't lost but is instead scrambled and spread across the black hole's surface. This process is incredibly complex, but it ensures that no information is ever truly destroyed. Some scientists even suggest that this scrambling of information could be linked to the phenomenon of quantum entanglement, where particles become interconnected in ways that defy classical physics. This connection could provide a bridge between the microscopic world of quantum mechanics and the macroscopic world of black holes. Of course, the holographic principle isn't without its challenges. Critics argue that while the idea is mathematically elegant, it's still far from being proven. Detecting the holographic nature of black holes would require observing phenomena that are currently beyond our technological capabilities. However, advancements in theoretical physics and observational tools, such as more sensitive gravitational wave detectors, could one day provide the evidence needed to test this groundbreaking idea. As we explore the holographic principle, we're not just learning about black holes, we're rethinking the very nature of space, time, and information. This theory invites us to consider that the universe might be far more interconnected and holographic than we ever imagined. And as we continue to probe the mysteries of black holes, we may find that they hold the key to understanding not just the cosmos, but the fabric of reality itself. Next, we'll explore how black holes might help scientists develop a unified theory of quantum gravity, bringing us one step closer to solving one of the greatest puzzles in physics. Now, let's take a closer look at how the holographic principle could fundamentally change our understanding of the universe. If black holes truly encode information on their surfaces like holograms, this idea doesn't just apply to these cosmic giants, it could extend to the entire cosmos. Imagine the universe itself as a vast hologram, where every event, every particle, and every interaction is encoded on a boundary we can't yet perceive. This radical idea suggests that the three-dimensional reality we experience might be a projection of information stored on a two-dimensional surface, much like a holographic image. This concept has profound implications for our understanding of space and time. If the universe operates like a hologram, it means that the fabric of reality might be far more interconnected than we realize. Space and time, which we often think of as fundamental, could instead emerge from deeper, more fundamental layers of information. This challenges the very foundations of physics, suggesting that what we perceive as the physical world might be a kind of illusion, a projection of data encoded on a cosmic boundary. One of the most exciting possibilities is that the holographic principle could help us solve the long-standing problem of unifying quantum mechanics and gravity. Quantum mechanics governs the behavior of particles on the smallest scales, while general relativity describes the large-scale structure of the universe. These two theories have been notoriously difficult to reconcile, but the holographic principle offers a potential bridge. By treating space and time as emergent phenomena arising from information, we might finally find a way to merge these two pillars of physics into a single, unified framework. But the implications go even further. If the universe is holographic, it could mean that information is the most fundamental building block of reality. This shifts our perspective from thinking of the universe as made up of particles and forces to seeing it as a vast network of information. In this view, black holes aren't just cosmic oddities, they're windows into the deeper informational structure of reality. They show us that information isn't lost but is instead preserved and transformed in ways we're only beginning to understand. Of course, this idea is still in its early stages and many questions remain. How exactly does information give rise to space and time? What is the nature of the boundary where this information is encoded, and how can we test these ideas experimentally? While we don't yet have all the answers, the holographic principle has already sparked a revolution in theoretical physics, inspiring new ways of thinking about the universe. As we continue to explore this theory, we're not just uncovering the secrets of black holes, we're redefining our understanding of reality itself. The holographic principle invites us to see the universe in a completely new light, where information is the key to unlocking the deepest mysteries of existence. And as we delve deeper into this idea, we may find that the cosmos is far more interconnected, more mysterious, and more holographic than we ever imagined. Next, we'll turn our attention to how black holes might help scientists develop a unified theory of quantum gravity, bringing us closer to solving one of the greatest puzzles in physics. Now, shifting our focus to one of the most profound challenges in modern physics, let's explore how black holes could hold the key to unlocking a unified theory of quantum gravity. For decades, scientists have struggled to reconcile the two great pillars of physics: quantum mechanics, which governs the behavior of particles on the smallest scales, and general relativity, which describes the large-scale structure of the universe, including black holes. These two theories work brilliantly in their own domains, but when it comes to understanding the extreme conditions inside black holes, they clash dramatically. This is where black holes become more than just cosmic mysteries. They become laboratories for testing new ideas about the nature of reality. At the heart of this challenge is the singularity, the point at the center of a black hole where gravity becomes infinitely strong and the laws of physics as we know them break down. General relativity predicts the existence of singularities, but quantum mechanics suggests that such infinities are impossible. This contradiction hints that a deeper theory, one that combines quantum mechanics and gravity, must exist. Black holes, with their intense gravitational fields and quantum effects at play, are the perfect testing ground for such a theory. One promising approach is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings could provide a framework for unifying quantum mechanics and gravity, and black holes offer a unique way to test these ideas. For instance, string theory predicts that black holes might have a fuzzball structure at their cores, where the singularity is replaced by a tangle of strings. This could resolve the paradoxes of singularities and provide a more complete picture of black hole interiors. Another avenue is loop quantum gravity, which suggests that space itself is made up of tiny, discrete loops. In this framework, black holes might not have singularities at all. Instead, their cores could be regions where space is so tightly woven that it prevents the formation of infinite densities. This idea not only challenges our understanding of black holes, but also offers a potential way to bridge the gap between quantum mechanics and gravity. But how can we test these theories? One possibility lies in the study of gravitational waves, the ripples in space-time caused by cataclysmic events like black hole collisions. By analyzing the signals from these collisions, scientists hope to find clues about the nature of black hole interiors and the behavior of gravity under extreme conditions. For example, if black holes do have a fuzzball structure or a loop-like core, the gravitational waves they produce might carry subtle signatures that differ from the predictions of classical general relativity. The quest for a unified theory of quantum gravity is far from over, but black holes are guiding us toward answers. They force us to confront the limits of our current understanding and push us to think in entirely new ways about space, time, and the fundamental nature of reality. As we continue to study these enigmatic objects, we're not just exploring the cosmos, we're rewriting the rules of physics itself. And in doing so, we may finally uncover the secrets of quantum gravity, bringing us closer to a complete picture of the universe. Next, we'll delve into the experimental approaches scientists are taking to test these groundbreaking theories and how black holes are at the center of this revolutionary quest. Now, let's turn our attention to the cutting-edge experiments and observations that are bringing these theoretical ideas about quantum gravity to life. Scientists around the world are using black holes as cosmic laboratories to test these groundbreaking theories, and the results could reshape our understanding of the universe. One of the most exciting tools in this quest is the detection of gravitational waves. These ripples in space-time, first observed in 2015, have opened a new window into the universe, allowing us to listen to the collisions of black holes and neutron stars. By analyzing the signals from these events, researchers hope to uncover subtle clues about the nature of black hole interiors and the behavior of gravity under extreme conditions. For example, if black holes truly have a fuzzball structure or a loop-like core, as predicted by string theory and loop quantum gravity, the gravitational waves they produce might carry unique signatures. These signatures could differ from the predictions of classical general relativity, offering evidence for new physics. Advanced detectors like LIGO and Virgo are constantly improving their sensitivity, making it possible to detect even fainter signals and extract more detailed information from these cosmic collisions. Another promising approach involves studying the shadows of black holes. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow, revealing the dark silhouette of the supermassive black hole at the center of the galaxy M87. By analyzing the properties of this shadow, scientists can test predictions about the behavior of space-time near black holes and look for deviations that might hint at quantum gravity effects. Future observations with even higher resolution could provide even more insights. Additionally, researchers are exploring the quantum properties of black holes through theoretical models and simulations. For instance, some studies suggest that black holes might emit faint quantum hair, subtle imprints of quantum information on their surfaces. Detecting these signals, though incredibly challenging, could provide direct evidence of quantum gravity at work. Other experiments focus on the Hawking radiation predicted to emanate from black holes, which could offer clues about how quantum mechanics and gravity interact. The search for quantum gravity is not limited to black holes alone. Particle accelerators like the Large Hadron Collider are also playing a role, recreating extreme conditions that mimic those near black holes. By studying the behavior of particles in these high-energy environments, scientists hope to uncover hints of the underlying quantum structure of spacetime. These experimental approaches are not just about testing theories, they're about pushing the boundaries of human knowledge. Every observation, every simulation, and every collision brings us closer to understanding the fundamental nature of reality. And as we continue to explore the mysteries of black holes, we're not just solving cosmic puzzles, we're rewriting the rules of physics itself. Next, we'll explore how black holes might be connected to another great cosmic mystery, dark energy. Now, shifting our gaze to one of the most profound mysteries of the cosmos, let's explore how black holes might be linked to dark energy, the enigmatic force behind the universe's accelerating expansion. This theory suggests that black holes could play a role in generating or influencing dark energy, offering a potential bridge between these two cosmic puzzles. Dark energy, which makes up about 68% of the universe, is responsible for pushing galaxies apart at an ever-increasing rate. Yet, despite its dominance, its origin remains one of the biggest questions in modern physics. Could black holes hold the key? Some researchers propose that black holes, particularly supermassive ones at the centers of galaxies, might contribute to the dark energy budget. One intriguing idea is that black holes could act as reservoirs of vacuum energy, a form of energy inherent to empty space that drives cosmic expansion. As black holes grow by consuming matter and merging with other black holes, they might release or store energy in ways that influence the universe's expansion rate. This connection could help explain why dark energy seems to dominate the universe today, even as black holes continue to evolve and interact with their surroundings. Another angle involves the interplay between black holes and the fabric of spacetime itself. According to Einstein's theory of general relativity, spacetime is dynamic and can stretch or warp under the influence of mass and energy. Black holes, with their immense gravitational pull, could create localized distortions that ripple outward, potentially contributing to the overall expansion of the universe. Some models even suggest that the energy stored within black holes might leak into the surrounding spacetime, subtly fueling the acceleration we observe. While these ideas are still speculative, they open up exciting possibilities for understanding the relationship between black holes and dark energy. Observational evidence, such as the growth rates of supermassive black holes over cosmic time, could provide clues. If black holes are indeed connected to dark energy, their evolution might mirror the universe's expansion history, offering a new way to test these theories. As we continue to probe the mysteries of black holes and dark energy, we're not just exploring the cosmos, we're uncovering the threads that weave the fabric of reality itself. Next, we'll delve into how black holes might hold secrets about the very beginning of the universe, the Big Bang. Now, let's turn our attention to the observational clues that might help us unravel the connection between black holes and dark energy. While the idea is compelling, proving this link requires more than just theoretical models. It demands concrete evidence from the cosmos. One promising avenue lies in studying the growth rates of supermassive black holes over billions of years. If black holes are indeed tied to dark energy, their growth patterns might align with the universe's expansion history, offering a potential fingerprint of this mysterious relationship. Astronomers have been meticulously tracking the masses of supermassive black holes at the hearts of galaxies, comparing them across different cosmic epochs. Interestingly, some studies suggest that these black holes grow faster than expected, especially in the early universe. This accelerated growth could hint at an energy exchange between black holes and the surrounding spacetime, possibly contributing to dark energy's influence. However, the challenge lies in distinguishing this effect from other factors, such as the availability of gas and stars for black holes to consume. Another piece of the puzzle comes from gravitational wave observations. When black holes collide, they send ripples through spacetime that can be detected by observatories like LIGO and Virgo. These collisions provide a unique window into the properties of black holes, including their masses and spins. If black holes are connected to dark energy, their mergers might leave subtle imprints in the gravitational wave signals, such as unexpected energy losses or distortions. Detecting these anomalies could offer indirect evidence of the black hole-dark energy link, though it remains a daunting task given the precision required. Cosmological surveys also play a crucial role in this investigation. By mapping the large-scale structure of the universe, how galaxies and galaxy clusters are distributed, scientists can trace the influence of dark energy over time. If black holes contribute to dark energy, their distribution and evolution should leave a detectable mark on this cosmic web. However, isolating this signal from other cosmological effects, such as dark matter's gravitational pull, is no small feat. It requires combining data from multiple sources, including galaxy surveys, black hole observations, and cosmic microwave background measurements. Despite these challenges, the potential rewards are immense. If black holes are indeed linked to dark energy, it would revolutionize our understanding of both phenomena, offering a unified framework to explain some of the universe's deepest mysteries. As we continue to gather data and refine our models, each new observation brings us one step closer to uncovering the truth. Next, we'll explore how black holes might hold clues to the very beginning of the universe, the Big Bang, and what that could mean for our understanding of cosmic origins. Now, shifting our gaze to the very origins of the cosmos, let's delve into the intriguing idea that black holes might hold secrets about the Big Bang itself. This theory suggests that these enigmatic objects could act as cosmic time capsules, preserving information about the universe's earliest moments. If true, black holes might offer us a unique window into the conditions that existed just after the Big Bang, a time when the universe was unimaginably hot, dense, and chaotic. One way black holes could connect to the Big Bang is through their singularities, the infinitely dense points at their cores. These singularities are thought to resemble the state of the universe at the moment of the Big Bang, where all matter and energy were compressed into an infinitesimally small point. By studying the properties of black hole singularities, scientists hope to gain insights into the physics that govern the universe's birth. However, this is no easy task, as the extreme conditions inside a black hole make direct observation impossible. Instead, researchers rely on theoretical models and indirect evidence to piece together the puzzle. Another fascinating angle is the role of black holes in the universe's early expansion. Some theories propose that primordial black holes, tiny black holes formed in the first moments after the Big Bang, could have played a crucial role in shaping the cosmos. These ancient black holes might have seeded the formation of galaxies and galaxy clusters, acting as gravitational anchors around which matter could accumulate. If primordial black holes exist, they could provide direct evidence of the universe's infancy, offering clues about the density and temperature of the early cosmos. Cosmic microwave background radiation, the faint afterglow of the Big Bang, also holds potential clues. This radiation carries imprints of the universe's earliest structures, and some scientists believe that black holes could have influenced its patterns. For instance, if primordial black holes were abundant in the early universe, their gravitational effects might have left subtle signatures in the cosmic microwave background. Detecting these signatures could help us understand not only the role of black holes in the Big Bang, but also the overall evolution of the universe. While the idea of black holes as cosmic time capsules is compelling, it's important to note that this theory is still in its early stages. Much of the evidence remains speculative, and researchers are actively working to refine their models and gather more data. Nonetheless, the possibility that black holes could unlock the secrets of the Big Bang is a tantalizing prospect, one that could reshape our understanding of the universe's origins. As we continue to explore this theory, each discovery brings us closer to unraveling the mysteries of the cosmos. Next, we'll examine how black holes might serve as vast information vaults, storing the history of the universe itself. Now, let's turn our attention to the cosmic microwave background radiation, often referred to as the CMB, and explore how black holes might leave their mark on this ancient echo of the Big Bang. The CMB is essentially the oldest light in the universe, a faint glow that fills the cosmos and serves as a snapshot of the universe when it was just 380,000 years old. This radiation carries subtle patterns and fluctuations that tell the story of the early universe, and some scientists believe black holes could have played a role in shaping these patterns. One intriguing possibility is that primordial black holes, those hypothetical tiny black holes formed in the universe's infancy, could have influenced the distribution of matter in the early cosmos. As these black holes moved through space, their immense gravitational pull might have caused ripples in the surrounding matter, creating slight variations in density. These variations would then imprint themselves onto the CMB, leaving behind faint but detectable signatures. If we could identify these signatures, it would not only confirm the existence of primordial black holes, but also provide a deeper understanding of how the universe evolved in its earliest moments. Another angle involves the way black holes interact with the fabric of spacetime. The intense gravitational fields around black holes can warp light and distort the paths of photons, an effect known as gravitational lensing. In the early universe, this lensing effect could have subtly altered the CMB, creating unique patterns that we might be able to detect today. By analyzing these patterns, scientists could gain insights into the distribution and behavior of black holes during the universe's formative years. This would offer a new perspective on how black holes contributed to the large-scale structure of the cosmos. However, detecting these subtle influences is no small feat. The CMB is incredibly uniform, with temperature variations on the order of 1 part in 100,000. Identifying the specific fingerprints of black holes within this delicate tapestry requires precise measurements and advanced theoretical models. Current and future missions like the Planck satellite and upcoming observatories are designed to map the CMB with unprecedented detail, potentially revealing these hidden clues. While the connection between black holes and the CMB is still largely theoretical, the implications are profound. If black holes did leave their mark on the cosmic microwave background, it would not only deepen our understanding of these mysterious objects, but also shed light on the universe's earliest moments. This interplay between black holes and the CMB represents a fascinating frontier in cosmology, one that could unlock new insights into the origins and evolution of the cosmos. Next, we'll explore the idea that black holes might serve as vast information vaults, storing the history of the universe itself. Now, shifting our focus to another groundbreaking idea, let's consider the possibility that black holes might serve as cosmic information vaults, preserving the history of the universe itself. This theory suggests that black holes could hold an immense amount of data, encoded in ways we are only beginning to understand. But how could something so destructive also act as a cosmic library? The answer lies in the intricate relationship between black holes and the laws of physics. At the heart of this theory is the concept of information conservation, a fundamental principle in physics that states information cannot be destroyed. When matter falls into a black hole, it doesn't simply vanish. Instead, its information, its properties, structure, and history might be stored on the black hole's event horizon, the boundary beyond which nothing can escape. This idea is rooted in the holographic principle, which proposes that all the information contained within a volume of space can be represented as a hologram on its boundary. In the case of a black hole, this boundary is its event horizon. One of the most fascinating aspects of this theory is the idea that black holes could encode information in the form of quantum bits or qubits, similar to how data is stored in a computer. These qubits would be incredibly tiny, existing at the Planck scale, the smallest possible unit of measurement in physics. The sheer density of information stored in this way would be staggering, potentially containing the entire history of everything that has ever fallen into the black hole. This raises the tantalizing possibility that black holes could act as time capsules, preserving a record of the universe's past. However, retrieving this information is another matter entirely. The intense gravitational forces near a black hole make it nearly impossible for anything, including information, to escape. This has led to the famous black hole information paradox, a puzzle that has baffled physicists for decades. If information cannot be destroyed, but it also cannot escape a black hole, where does it go? Some theories suggest that information might slowly leak out over time through a process called Hawking radiation, named after the renowned physicist Stephen Hawking. Others propose that the information remains trapped inside the black hole, forever inaccessible to the outside universe. Despite these challenges, the idea of black holes as information vaults has profound implications. If we could somehow decode the information stored within them, it could provide a window into the universe's earliest moments, revealing secrets about the formation of galaxies, the nature of dark matter, and even the origins of life itself. This theory also bridges the gap between quantum mechanics and general relativity, two of the most successful but seemingly incompatible frameworks in physics. By studying black holes as information repositories, scientists hope to uncover a unified theory that explains the fundamental workings of the universe. As we continue to explore this fascinating concept, the next section will delve into whether it's possible to retrieve information from black holes and what that could mean for our understanding of physics and the cosmos. Now, let's turn our attention to one of the most intriguing questions surrounding black holes as information vaults. Is it possible to retrieve the data they hold? The idea of accessing information from a black hole might sound like science fiction, but it's a question that has serious implications for our understanding of physics. If black holes truly store the history of the universe, finding a way to decode that information could revolutionize science as we know it. One of the key challenges in retrieving information from a black hole lies in its event horizon. This boundary acts as a one-way gate. Once something crosses it, it's seemingly lost forever. However, some theories suggest that information might not be completely trapped. For instance, Stephen Hawking proposed that black holes emit radiation over time, a phenomenon now known as Hawking radiation. This radiation is thought to carry away tiny amounts of energy from the black hole, causing it to slowly evaporate. Some physicists believe that this process could also allow information to escape, encoded in the radiation itself. If true, this would mean that black holes aren't entirely black. They might slowly leak their secrets back into the universe. But here's the catch: even if information does escape through Hawking radiation, decoding it would be an extraordinary challenge. The radiation is incredibly faint and mixed with random noise, making it nearly impossible to extract meaningful data with our current technology. Additionally, the process of retrieving this information would require an understanding of quantum mechanics and gravity that we don't yet possess. This has led some scientists to speculate that retrieving information from a black hole might require entirely new physics, potentially bridging the gap between quantum theory and general relativity. Another fascinating idea is the concept of quantum entanglement. Some researchers suggest that particles falling into a black hole could become entangled with particles outside of it, creating a kind of quantum link. If this link could be harnessed, it might provide a way to access information from within the black hole without directly crossing the event horizon. However, this remains purely theoretical, and the practical challenges of such a process are immense. The implications of successfully retrieving information from a black hole are staggering. It could provide insights into the earliest moments of the universe, shedding light on the Big Bang and the formation of galaxies. It might also help us understand the nature of dark matter and dark energy, two of the greatest mysteries in modern physics. Furthermore, it could lead to breakthroughs in quantum computing, as black holes are thought to process information in ways that resemble quantum systems. As we ponder these possibilities, it's clear that the quest to retrieve information from black holes is not just about solving a scientific puzzle, it's about unlocking the secrets of the cosmos itself. And with that, we move to our next theory, which explores how black holes might be connected to the mysterious force driving the universe's expansion, dark energy. As we reach the end of our journey through these 25 groundbreaking theories about black holes, it's clear that these cosmic enigmas are far more than just gravitational traps. From the possibility of black holes acting as wormholes to other universes, to their potential role as dark matter factories, each theory challenges our understanding of space, time, and reality itself. We've explored how black holes might function as quantum computers, store the universe's history, or even reveal hidden dimensions through their collisions. And let's not forget the tantalizing idea that they could be connected to dark energy, the mysterious force driving the universe's expansion. These theories don't just push the boundaries of science, they invite us to rethink everything we thought we knew about the cosmos. Whether it's the holographic principle suggesting that black holes encode information on their surfaces, or the idea that they might hold clues about the Big Bang, each concept opens up new avenues for exploration and discovery. The study of black holes isn't just about understanding these singular objects. It's about unlocking the secrets of the universe itself, but the journey doesn't end here. Science is a constantly evolving field, and every new discovery brings us closer to unraveling these cosmic mysteries. So, what do you think? Which of these theories fascinates you the most? Do you believe black holes could be the key to understanding dark energy, or do you think they might hold the answers to time travel? Share your thoughts in the comments below. We'd love to hear your ideas and theories. If you enjoyed this deep dive into the mysteries of black holes, don't forget to hit the like button, subscribe to the channel, and turn on notifications so you never miss an update. There's so much more to explore, from the latest discoveries in astrophysics to the mind-bending theories that challenge our understanding of reality. Thanks for joining us on this cosmic adventure, and remember, the universe is full of wonders waiting to be uncovered. Until next time, keep looking.